Okay. All right, so we're resuming from where we left off before the midterm, where we started discussing a different style of problem like SAT and 2SAT were the topics in particular. Today we're going to talk about a simple problem called subset sum. Yeah, let me maybe quickly review, because I imagine you put every effort to forget this over the past week. So, right. So SAT, this is just kind of Boolean logic kind of situations and or nots and things like this. And the basic problem is I give you like a simple looking Boolean formula. And can you find some input that makes it come out to be true? Okay. And that's it. You can have special cases like CNF, which means it's always an and of ors. So little clauses have ors in it. 3SAT will have exactly 3 variables in each of those ors. And what we found was, even with all these special cases, there's a polynomial time algorithm for one, even if there's a polynomial time algorithm for all. Okay. Some of those problems seem very general, like circuit SAT and general SAT, so that wasn't so surprising. Maybe it's more surprising that even when you get down to specific things like 3SAT, the tractability doesn't seem to change. On Thursday, we did 2SAT, which was even more special, right? So now you have 2 variables in every clause instead of 3. We looked at 2 variations of the problem. One is just trying to satisfy all of them, and the other is trying to satisfy as much as possible. For both, you can ask this question of like, is there an algorithm or is there not? And what we found was that for 2SAT, you can do an algorithm if you actually build up a certain kind of graph based on like, oh, if I set this to be true, then that has to be false or something. There's like some kind of like one-way implications. And you can kind of tease apart what does a connected component mean in this graph and things like this. And you can actually solve 2SAT in your time. But if you're doing max 2SAT, all I'm saying is now instead of trying to satisfy everything, you're trying to satisfy as much as possible. Things took a dramatic turn. And we actually found with some, very clever techniques that you can actually take a 3SAT problem and encode it as a max 2SAT problem. Okay, and of course the exact details are not really as important, but anyway, so you do some kind of reduction where ultimately max 2SAT can be used to solve 3SAT. Okay, and sort of like details aside, there's a very clever algorithm, there's a very clever reduction, but I think the real thing is like, oh, here are 2 very similar problems with completely different characteristics. There's something a little more subtle about this, notion of polynomial time algorithm that maybe meets the eye. Okay, and that's sort of what we are continuing today. So here is kind of a special case of the problem we're looking at today, which actually, I'm not really sure. With each subsequent class, it's not clear if you've ever dealt with real change anymore. In America, a quarter is worth 25 cents. There's these things called cents. And you used to buy things that cost less than $1. But there's quarters that are worth 25 cents, dimes that are 10 cents, nickels that are 5, a penny is 1. Did we get rid of the penny? Yeah. Is that a thing?
It's not existed.
Yeah, so it's not clear that this will ever come up anymore. And I'm not sure what they're going to do about everything that costs something 99 cents. But in any case, it's a theory class, so we don't have to have real pennies. If I gave you 93 cents and you wanted to exchange it put it into coins, what would you do? So maybe I'll just go through them one by one. You just tell me how many of each coin. So quarters. 3. How about dimes? 1. Nickels. 1. Yeah, okay. So I think this will add up to 93 in a bygone era. Okay, so that's basically the kind of problem we're looking at here. It's very simple. I'm going to give you as input n integers. Okay, and then I'm going to give you a target value. And I'm just going to say, can you get a subset of those values that adds up to the target? Okay, so here's like here's an example. Here's a bunch of numbers, and your target is 52. Is there a subset of those numbers that adds up to 52? Now, I should know, unlike coin changing, you can only use each number once. All right, so I'll let you stare at it. I actually don't remember the answer, so hopefully you'll figure it out. Yeah, 14, 13, 11, 10, 4. Is that what you said? Okay, let's check. 27, 31, 42, 52. Sounds good. Anyone get another one? I'm not sure if it's, yeah. 14, 18, and 18. 36, 52. Okay. Yeah, I guess that means you can also like start getting things to add up. Like I can take this 18 and turn it into 11 and 7. That would give another solution, I guess. I don't know. Okay. So that's the problem. So in many ways, it's like a very simple problem, right? We're just adding up numbers. But I should at least point out that it's a search problem in the sense that it takes some effort to maybe stare at it. But when someone proposes a solution, it's very easy for me to check. Even I can check, in front of you in the class, just try to add up to 52. Yeah, not that I haven't messed that up before, but in any case, it's easier to check than to find a solution. So, okay. So we're going to do the usual vote, or usual from before the midterm. So we're going to either try to figure out if there's an algorithm, or if it's going to turn out to be tough like SAT, or you don't have to vote. Okay. So first, who's not going to vote? One TA. Thanks for that. Okay. Okay. So now the remaining choices are polynomial time, or you're going to think it's hard. Okay. Who thinks we're going to get an algorithm? I would say that's the majority. Okay. Who thinks it'll turn out to be hard? Okay. So it was pretty close to even, slightly more in favor of coming up with an algorithm. Okay. Well, let's start with algorithm then. If I wanted to make an algorithm, how might I start? Yeah. Okay, so at a high level, we can try to do DP, but let's start with a recursive spec then. All right, so if I'm going to do a DP, let's just come up with a name, some parameters, and we'll just solve the algorithm. So anyone want to propose a name or an acronym? Yeah. All right, subset sum. All right, SS. All right, so we need some parameters. Sorry? Okay, so you're given an array of elements, something like this, array of numbers, and a target, call that T. Okay, and then the sentence would be, yeah, so like, yeah.
Target T returns whether or not a subset exists. That sums up to T.
All right, so given whatever, you describe the input a little bit, target T. So return true if a subset sums to T and maybe false otherwise. I think it's good to clarify that you're returning a true false here because you're going to want that in your recursive calls. Okay. All right. That's basically what I had. Yeah, something like this. Okay. All right. Let's implement it. Yeah.
First, you do it's basically just include exclude. So we call subset sum on. I guess the base case would be if t is less than 0 or equal, or if t is less than 0, return false. If t equals 0, return true.
Okay.
And then you call subset sum on x or from like 2 to n. And then you do t minus x1. And you do that or subset sum x2 to xn t.
Something like this. Return. Okay. So what's the idea? So you're trying to add up to t. If t is less than 0, and here I in the input I said all the things are positive integers. So if t is less than 0, then you know it's false. And if t is 0, then you have already got the sum, right? You could just return nothing that captures the sum. So that's true. Otherwise, I'm going to basically guess if x1 is in the solution or not. So I might, on one hand, try subtracting x1 from t. That's like taking x1 and seeing if the remainder can get that remainder. Or you don't use x1 and just see if x2 through xn can capture t. Okay, one tiny bug, not a big deal, but yeah.
Maybe you like loop through all the numbers and t is still greater than 0, but the array is empty now.
Yeah, so there's a small chance that n is 0. So I guess if you're already down here, you know that t is not 0. So if n is equal to 0, return false. Something like this. Okay. All right, so yeah, if you have no numbers left and your target is non-zero, then you should be returning false. Okay, so I think that's roughly what, that's exactly what I had. Okay, so simple enough. Now, what's the running time of our algorithm? Yeah. Sorry? Okay, sorry. So yeah, if you don't do any caching and stuff, you just ran this naively, then it'll take 2 to the n or something because you're trying everything. But if you did apply dynamic programming, so you're saving all the parameters, then what does our running time look like? Yeah. Tn. So why? Where does the n and where does the t come from? Yeah, so n because you're always looking at kind of remaining suffixes of your original input of n, the last 10, the last 9, the last 8. And t because that's your original target and you're just subtracting from there. And if you ever go below 0, you just return right away so that you don't have to pay for it. So, all right, so you just get a big O n of t running time. In fact, I think this is basically an easier version of like subset subs roughly, but okay. All right, so good. All right, so you get yeah. So with dynamic programming, you'll get big O nt time. Okay. All right, here I think I've only just re-indexed this, so it's easier to see kind of how it's getting saved. But this is referring to numbers I plus 1 through n and numbers I through n. Okay, so that's simple enough. I think that's what you're used to. Okay, so going back to our thing, we had roughly 58. What did I say? 42? Okay. Okay, I don't know why I'm belaboring this point. Okay, so all right. So are we happy with a big O NT running time? Yeah.
Right. Why are there NT subproblems? Isn't it like combinatorially many pair like subsets of groups?
Okay, so I think it's good to maybe look at this formulation. So here I've re-indexed things so that the first argument is just I, and it's saying, okay, I'm trying to make a subset out of numbers xi through xn. So in this version, you can see I'm always looking at a suffix of the n numbers. So I've already processed 5, and there's n minus 5 remaining. I've processed 10, there's n minus 10 remaining. So for that, there's only n problems. And then the t is coming from the target value, starting at t and then just going down from there.
So we're assuming that elements are at least one in value.
Yeah, but yes, we're assuming the elements are at least 1 in value, but I think that's not necessary either. Because like, let's say that the value was 0, I would still look at all the remaining numbers trying to add up to s, or all the remaining numbers add up to s, but all the remaining numbers will still give me like a smaller problem. Because at least I got rid of that problem, that number I was focusing on. So sort of like, it's like edit distance and like common subsequence problems. We're just kind of munching down like Pac-Man, eating away from the beginning of the list. And we're only looking at these suffixes. So that only gives you n suffixes. Yeah. Okay, so that's fine. The real question though is, do we have a polynomial running time? Yeah,
Depends on T.
it depends on t. So exactly. So t takes log t bits to write down. Now you've had a couple exercises already where I said, that's okay. That t is going to be at most n or something like this, like on the midterm. But in general, t could be 2 to the n, right? Like, and it would just be n bits long, and so your input size wouldn't get much larger. Okay, but your running time would suddenly start looking exponential. So, right, okay, so if t starts to look like 2 to the n, then we actually have an exponential running time. We don't really have a polynomial time algorithm yet. Okay. So, that said, any other ideas? Any ideas to try to fix this dependency on t? Okay, I think that's the right answer. So we're going to flip over, and we're going to instead try to show that maybe it's as hard as SAT. Okay, so right, so and this is kind of normal, right? You encounter a problem, it seems pretty simple. You try your standard techniques, doesn't quite get us there. Okay, let's try flipping over. Okay, but one thing that maybe is a departure from our previous lectures. We did like 3SAT, we did 2SAT, we did max 2SAT. Max 2SAT at least looks a little bit like 3SAT because it's still SAT. But subset sum looks nothing like SAT. So this would be a much bigger jump, conceptually, if that turned out to be the case. Okay. Nonetheless, that's what we're going to try to do. So our theorem that we're going to spend the rest of class proving is that a polynomial time algorithm for subset sum will give you a polynomial time algorithm for SAT. So that should be surprising if you haven't seen it before. Okay. That makes high-level pictures okay? All right. Any ideas? Yeah.
We know that a variable's either just sum or not. Speculate it's been some that represent true, it's not some that represent false. That's not given by log of one variable, some variable.
Okay, that's a great start. So one second, let me maybe set this up a little bit. So we'll start from 3SAT. We already know that 3SAT can solve general SAT, so we can just start from 3SAT, right? And then, just to skip ahead, we'll somehow want to take our 3SAT formula, turn it into numbers and a target, so that if you feed it to the black box for subset sum, and it gives back your yes or no answer, you can somehow interpret that for SAT, right? So we want to just to be clear, we'll start with a 3-sat formula. 3-sat's sort of convenient because there's only 3. And we somehow want to create a subset sum type of problem. And so I think the suggestion is a great start because the first thing is to like try to map choices to choices, right? And so the suggestion was like, well, maybe every variable in the formula, setting it to be true or false, those are our choices, can correspond to sort of taking a number or not taking a number. So maybe each variable will map to a number that's like a reasonable kind of pattern matching way to get us, just to make kind of the high level syntax match. That seems like a reasonable start. Okay, so we could try something like that. At some level, you're either taking numbers or not. But beyond that, what? Well, at some level, we also have to figure out some T. We have to somehow encode actually taking the clauses or satisfying the clauses, I mean. Yeah. Okay, so the suggestion paraphrasing was something like, well, adding 2 numbers is also doing something with the bits, right? And then equal numbers is something to do with equal bits. That was roughly what you're saying? Okay, and indeed, so that's going to be, I think, the big sort of idea in this lecture. Is that, okay, at some level, subset sum seems so simple because you're adding numbers. You've done that your whole life. You're just adding quarters and nickels and dimes and no longer pennies, but you still add up the rest. And what we're going to leverage is the fact is that numbers are bit strings too. Okay, and there's just like lots of bits. And for 2 numbers to be equal, all the bits have to, of course, match up. And what we're going to do, we're going to be very clever. We're going to use many digits. Right? If I have an n variable sat formula, I can create n-digit numbers, and that's fine. And each digit is going to sort of encode one piece of logic, something that has to be satisfied, so that somehow in the subset sum problem, we put it all together. If all the bits match, it'll kind of satisfy all the logical requirements of our sat formula at some level. So we're going to use each sort of digit to encode something about the sat problem, and they'll all have to be equal, and then, yeah, it'll be a little bit messy, or it'll certainly appear alien, but that's the idea, is that actually you can pack a lot of logic into what would seemingly be sort of benign numbers. So, okay, so, good. All right, so I think the first thing I'll try to do as just a warm-up before even getting to subset sum, I'm just going to try to re-express 3-sat in a slightly more subsetty language. So nothing too deep going on here. So what I'm going to think about is like I'm choosing to set x1 to be true or x1 to be false, but some of them I'm choosing one or the other. So I'm thinking of like, okay, I'm let x sort of refer to these literals. And then I'm going to think of each clause, which is normally 3 variables, sometimes negated. I'll think of it as a set of 3 literals, which is maybe how you already thought of it. I'm just making it a little bit more explicit. Okay. And right, in this terminology, it's sort of like, okay, can I find some subset of the literals? Right, so I can choose x1 or x1 bar or x2 or x2 bar. I'm trying to choose some subset, and I only have basically 2 rules. The first rule, let's see actually what is the first rule. Okay, the first rule I think is natural. For every clause, I need to choose one of those literals that appear in it. That's like, if I choose x1 bar, that's like setting x1 to be false. Okay, so I'm just trying to formulate this as some kind of subset looking thing. Set, I'm just trying to inject the word set into sat. So I'm thinking of each clause as a set of which I need to take one or something like this. And what would be the other rule? Like right now, nothing prevents us from just taking all the literals. Yeah. Oh no, that's okay. So each clause has 3, but that's part of the input. I'm trying to kind of create a new problem with certain rules. Maybe this is an awkward question. Forget it. Okay, the other rule is like, so I'm going to choose a subset of literals, just like I'm choosing a subset sum or something. But for every xj, I'm going to only be allowed to take one of the two literals. Okay, so this is just some kind of like bridge to get me closer to something that's easier to approach from a subset sum point of view. I've kind of just recast, renamed things from 3SAT, where I think of each clause as, just containing three symbols, x1 or x1 bar or something like this. And I want to choose a subset of those symbols, but I'm not allowed to take any opposite symbols. Okay, so symbols are literals, and each clause is just a set of three of these symbols or literals. Okay. All right, so that'll make it a little bit easier to do the more interesting part. That's the same slide. Okay, so maybe, all right. So, okay, so now what we're gonna do. So at some level here, we're choosing symbols or literals, and in subset sum, we're choosing numbers. So I want to somehow start, I didn't do a good job here, okay. Okay, so what's the idea? Now we're gonna start creating numbers for our actual subset sum problem. So what we're gonna do is we're gonna make a ton of digits. And I'm gonna do it base 4 because you'll see it's a little more convenient to do it base 4 than doing base 2 because then you'd have to like worry about carrying or something like this. I could have done it base 10. Any constant would have been fine. 4, I think we'll see is enough. And it's gonna be a lot of digits. And in fact, we'll have one slot for every clause and one slot for every variable. So that's kind of the high level structure. And so for every literal, we're going to want to make a number. So, okay. So we have, for every variable xj, we have xj and xj bar, and each of those will be turned into some kind of number. Here, I'm just worried about xj. We'll do xj bar next, so only one thing will change. So for xj, I'm going to make some number, I'll call it aj. Okay. It's going to have a bunch of digits. The only remaining question is, what are the values I'm going to put in the digit? So I'm not sure if this is guessable, if anyone wants to propose maybe a sensible way to try to sort of map each symbol or literal to a number. I don't know if this is guessable, but gives you a chance to process. Yeah.
That's gonna make sense, but if you are literal in clause I, and you are the J element in clause I, then you can just set the like ith bit. Well, in this case, base 4, but
I understand.
ith bit in the clause to true, and then the jth bit in the slot on the right to true as well. And so that would kind of create like that meaning that requires whichever. I guess if a variable appears in multiple places, then I don't know if you can like overlap them and still be unique.
I think that's actually quite close to what we'll kind of do. So what we'll do, okay, so I have some variable xj, and it's in some of the clauses. Actually, let me do the easier one first. The first one, let me do the bottom one first. So what I'm going to do is I'm going to set, so I have one slot for every variable. So at some level, all the variables kind of share all these spaces. But the xjth variable is going to mark a 1 in the slot corresponding to the jth variable and 0 everywhere else. It's sort of like declaring I am one of the literals for variable xj. And then maybe the more interesting part is the part where we mark all the clauses that it's in. So for every clause ci that contains xj, it's going to correspond to some, so I have these m slots, one for every clause. And if that clause contains the variable, I'm going to put a 1 there. sorry. I'm going to put a 1 there. And if it doesn't contain the variable, I'm going to put a 0. Okay? So, so you have all these 0, 1, 0, 1, 0, 1s. We haven't used actually the full 4 yet. That'll come later when we start summing things. But at some level, like, so I have this literal xj that sort of represents setting xj to be true. And I'm creating this number where at some level you can kind of read off like, oh, these are all the clauses where xj appears. And it's one of the literals for the jth variable. Okay, so it might feel a little magical still because we haven't seen the full picture, but that's the construction. So I'm going to mark every clause that the variable appears as xj, not xj bar. I'll put a 1 there. Everything else will be a 0. Okay. And then on those last n slots, 1 for every variable, I'll put a 1 in the j slot, the 1 corresponding to the xj variable, and a 0 otherwise. Okay. So it's some very large number that's sort of encoding, everything it's doing, basically. Okay. Yeah.
Code xj bar.
Okay, so how should we encode xj bar? In fact, we're going to do basically the same thing. Xj bar, I'm going to put a 1 in all the clauses that it appears as xj bar, not as xj. So that will be different clauses. In general, you won't have xj and xj bar in the same clause because that clause is automatically satisfied. So this will be a different set of 1s in the first m slots. And I'll still put a 1 in the j slot to mark this is a literal for that jth variable. It's now xj bar instead of xj, but the point is. Okay. So at some level, the same thing. But they'll naturally be in different clauses. Yeah.
Are m? Do we know what m is again though?
So m is a number of clauses in our input formula, and n is the number of variables. So we know that. It's just the size of our input. Yeah, so for every clause, I have a digit. For every variable, I have a digit. I'm just kind of packing in information, right? Somehow, I'm taking a whole SAT problem and stuffing it into some numbers. Okay, so good. All right, so going back to this set formulation of 3 SAT, right? You want to choose a subset of the literals so that A, you take at least 1 literal from every clause, and you take exactly 1 of xj or xj bar for every j. Okay, so those are kind of the 2 rules. And what I want to do is try to translate those rules into some kind of some subset, some terminology, kind of conceptually, as we gradually go from one problem to the other. Right? And at some level, this is sort of a big leap because we're really going from between 2 problems that look nothing like each other. So it should feel a little bit weird. Okay, so we just showed, that every literal is going to map to one of these long numbers. X1 is going to map to this long number A1. X1 bar is going to map to this long number A1 bar, based on that system we came up with. So we'll have 2 n numbers, 1 for every literal, X1, X1 bar, X2, X2 bar. Okay. Now, we're thinking of like taking a literal as like taking a number and adding it to our sum, right? So choosing a set of literals is going to kind of map to the sum of the corresponding numbers, right? So for every subset of literals, I took x1 and I took x2 bar and I took x3. We can look at the corresponding sum where I'm kind of adding up all those crazy long numbers. I'll call that D. Okay. All right, so now we have 2 constraints on S, the set of literals we take. And what I want us to do is try to kind of express that in sort of the numerical language, set up by the first 2 rows, if that makes sense. Like maybe the last row is easier again. So, I have constraints saying, look, I can only take 1 of xj or xj bar for every j. And I want to rewrite that as summation saying, there's something that has to be true about the sum D of the numbers I took. So based on our kind of transformation, how can I express this rule in terms of our sum d? Yeah.
Top, then the first m bits will have to be 1, so that means you pick at least something from each.
Okay, so you're saying, wait, sorry.
The
What?
m bits on the
Oh,
bits
okay.
on the left.
All right, so we can do the second to last row then. Okay, so that would be more about constraints, right? Okay, so this one is saying, look, for every constraint, you have to take at least one. And then in terms of our summation, you're saying that the first m bits all need to be,
All need to be 1, meaning that you picked
You-
at least one item from each.
so if it's if you're saying it has to be equal to one, is that saying that you picked one or saying you picked at least one?
Saying that you picked an odd number of them, so yeah, I guess.
Well, it's modulo 4, so it's either 1, 2, or 3. But we're basically very close. So at some level, so basically, if I just wanted to read off, if suppose you only had D, access to D, and you're trying to figure out, oh, did I satisfy these rules? And you're just looking at the digits, right? How can I look at the digits of D and conclude that every constraint was satisfied? I took at least one literal from every constraint. So you just have this big number, yeah.
All of them are threes.
If all of them are threes, that means you got 3 literals from every single one, right? Because each one adds 1. Yeah.
There's at least one from each of the bits in the like at thousands, so like 1 or 2 or 3. But if any of that's 0, then it indicates that there's one constraint that's not.
Great. So yeah, so sort of in between all the suggestions, but that was it. We need to make sure each of those sort of base 4 digits or whatever the word is, quits. I don't know. Has at least 1. It could be up to 3 because there's only 3 variables in each clause, but you want to make sure they're not 0. So you want to make sure that for each of those first m digit thingies, the digit corresponding to that clause is at least 1. Right? Because every time you took a literal that appears in the clause, you get to add 1 to each of those clauses. Okay, so that's what, yeah, it's just worth going slowly because I know this is sort of like a completely bizarre thing that we're doing. But since we put a 1 every time in every clause the literal appears, if I take that literal, you get 1s in all those digits. So by making sure you have at least 1 in each of the clause digits, that's really saying you took at least 1 for every literal. Okay, so it's kind of going back and forth. Okay. Now, what about this last rule? This last rule says I'm only allowed to take xj or xj bar for every variable. How can I sort of, if I have this, I take some numbers and I have this huge sum d, how can I look at d and say, oh, yeah, I can see very clearly that you took exactly 1 for each literal? Yeah. Yeah, so when you say they are all equal to 1, in particular those last n digits, right? We had those n digits, 1 for every variable, and we're only allowed to take 1 literal for each one. And if we look back, aj had a 1 in that slot for variable xj, and aj bar or not aj or whatever also had a 1 there. So if you had taken both, you would have gotten 2. If you had taken none, you would have gotten 0. If you take 1, you'll get 1. Okay. So looking at those last n digits, 1 allocated for every variable in your sum, you can see, oh yeah, you did take exactly 1 literal for each one because it's the only way to get all 1s. Okay, so we're just kind of encoding this sort of yes or no, take it or not take it, at least 1, whatever, logic into a bunch of small numbers and just laying them side by side and packing them into these integers. Okay. All right, so, okay, good. Now, okay, so if I look at this right column, at least I've sort of taken 3 side. I can express it sort of numerically in terms of these numbers and stuff like this, but we don't quite have a subset sum problem. What is the gap? So we don't really have a target yet, right? We need a target, but in particular, why doesn't this give you a target? Yeah.
Multiple possible targets.
Yeah, so there's multiple possible targets as laid out here, and where does that kind of multiplicity come from? Yeah. The blue one, yeah. So this greater than or equal to 1. This bottom row looks perfect for a subset sum, right? Like, oh, this is going to be exactly 1. But up here it's saying, oh, those digits have to be at least 1. That doesn't really feel like this equal sum kind of thing, right? But we're getting awfully close, right? We just have to figure out how to fix this issue of, yeah. We can make what?
The CI's digit equal to 1 instead of not equal.
Instead of what?
The blue constraint,
Yeah.
we can just pick it to be equal to 1 exactly instead of allowing us to like take more.
Okay. So if I set it equal to be 1, then and I flip back to what does that mean for 3 sat? Okay, so suggestion is like, okay, so why don't we just say it has to be equal to 1. Now, if I kind of translate back to our 3 sat problem, that would be saying that you have to take out exactly 1 literal from every clause, which I think you actually saw as a problem in PSO, maybe 1 in 3 sat. But normally in 3 sat, you just need to make sure you take at least 1. So if we force that digit to be 1 and said, that's my target, those have to be equal to 1, we sort of now are solving a different problem. It is true that you'll get a subset sum, and in that sense you'll be happy, but you'll be using subset sum to solve not quite the problem you want to solve, because it's asking if you can figure out how to set exactly 1 literal to be true in every clause. Yeah.
So just to understand, the literals X and SAT correspond to taking out a number in our array.
Yes.
Okay.
Yeah, so that's the correspondence, right? We kind of went from, well, 3 sat, you normally set variables to be true or false. We first think of that as sort of taking x1 to be true or taking x1 to be false. And each of the choices map to a number. So actually, the original suggestion, the beginning of class was like, oh, setting to be true should take a number, and then setting to be false is omit the number. We're doing something slightly different. We have one number that represents setting it to be true, and a different number that represents setting it to be false. Although this bottom line set of kind of digit constraints forces you to choose exactly one of those two.
So then how are we actually holding the values of those numbers in like the original array into literals? Like the literals don't actually encode the value of the numbers.
Oh, sure. So if we did this very slowly, I would get this SAT formula, right? And now I just need to make all the numbers. So I take x1 and I make this m plus n digit number where I go through and I see which clause it appears in. I put a 1 in those digits. I put a 0 everywhere else. And I put a 1 because it's in the xjth one. So I just build them slowly in a loop. So every variable, you just loop over the formula.
No, but like once you get to A1, right?
Yeah.
A1 doesn't say whether or not the number in the array is a 5, a 7, a 10. Like you don't know if you sum a bunch of these numbers together that you picked, it doesn't actually tell you what your final sum is if you pick those numbers. Right? I don't know if I understand.
Okay. So that's true. Are we solving a question of like finding the true or false that satisfies it, or just trying to figure out if it's satisfiable? Am I trying to get the actual numbers that add up to the target, or just figure out if there is a subset? And we discussed this a little bit, but some level, if you can, so one lazy way out is if you can solve the yes/no question, you can always solve this sort of construction or search question. So imagine you could only do the yes/no version of subset sum. How could you actually use that as a black box to extract sort of the underlying numbers of a solution? Yeah, you just try, I'll try x1, I'll subtract it from t, and I'll see if the remaining problem is still solvable. So if you can do yes, no for either, then you can always extract a solution. So we don't have to worry about that too much. Plus, I think if you look closely, you can just whatever, adjust the algorithm to remember a little extra information. It's not that big a deal. Okay, all right. But going back to this point, I would really like to come up with a single target or something like a target where I'm just trying to make it equal. And right now we've gone very close. I've sort of mapped all the choices I can make, the numbers I can take, and I can sort of describe all the constraints of my 3-sat problem, at least numerically, one set of equals and then one set of greater than equals. And if I could figure out how to take that greater than equal, turn it into some kind of equal, then it'll be clear how to make a target. Are we okay? Yeah. So just one last sort of technical detail, one last moment to be clever, but we've already done a lot of conceptual progress. I would argue maybe most of the hard work has been done, which is just this big conceptual leap from logic or complex logic to numbers. Right? But anyway, but now what's left is sort of a puzzle. Any ideas for how to take our subset sum problem or the beginnings of our subset sum problem and really flesh it out into a real subset sum problem that'll solve our original 3-SAT? It's very clever, but it's not necessarily a super complicated thing, so it's kind of guessable. Not easily guessable, but. Is the question okay? I mean, you have a lot of degrees of freedom. You can add more numbers, you can do whatever you want as long as it produces a subset sum problem. Okay, I'll give a hint. You're going to try to, one thing that you are going to do, or at least we're going to do, as the slides are set up, is we're going to introduce more numbers to the problem that kind of are just convenient, right? They should make it so that you can kind of fix a 1, 2, or 3. At some level, we don't want to strongly distinguish between 1, 2, or 3 for each of those digits, right? They're all kind of equally good for satisfying a clause. So if I could maybe add in some sort of junk numbers that sort of lets me fix certain things. I don't know if that helps. It's fun to guess before I get the answer, so. Yeah,
maybe numbers to assess how many, like, I don't know, like 1, 2, or 3, but not 1, 2, or 3, but like additional numbers to suggest how many of the like digits and constraints are satisfied.
yes, some kind of additional numbers. I think you're getting really close. Did you have an idea or? No? Any- Yeah,
Just a clarifying question. Like, are you saying that we have to have like all the D's being the same, like numbers, so either 1, 2, or 3?
yeah. So I think kind of semantically, in terms of our 3-SAT problem, right? We're happy if we get 1, 2, or 3 literals. So at some level, we're okay if that digit is 1, 2, or 3. But the way subset sum works is like I can only add equality constraints, right? I can only say this digit has to be equal to that, and that digit has to be equal to that. So this 1, 2, or 3 is a little bit jarring, right? And if I could figure out, maybe I can add some numbers and then say that digit has to be equal to this, right? Yeah.
You could do like the division so that if
Sorry?
number
You can
is
do.
greater than 1, it return 1.
So yeah. So you can say it again.
I was thinking like it could be 1, 2, or 3, right? They all satisfy our constraints.
Yeah.
So we could do like division by 3 and then do the ceiling of that, so that 1, 2, or 3 returns 1, but 0 will return 0.
Okay. So division by 3. Okay. So 1. So yeah. How does that work? 1 divided by 3 is.
If you do a ceiling of that, it will go to it.
Oh, okay. So if yeah, okay. So it's like, okay. Yeah, I mean, at some level, you're also trying to distinguish non-zero, right? So 1 divided by 3, 2 divided by 3, and 3 divided by 3, and it would all round up to 1 or something, if you're allowed to. Yeah, but I think we're not allowed to, I think, do the ceiling and division trick. But yeah, but I think it brings up a nice point, which we're also just trying to distinguish non-zero from, yeah.
Under the two assumptions that there is no carryover from one digit to another, and that if you go past 3, you can cycle back, then you can definitely just add a bunch of numbers which are all 0 and like the red digits on the right, and are some combinations of like 0, 1, 2, 3 on the other cases, so that like you can, depending on whatever your solution for D is, you choose an extra number, which when you add it, says all of these in one.
Okay, so I think that's on the right path, but there's maybe something simpler, but along these ideas. Can I add some numbers so that maybe I can fix my 1 and turn it into a 3? I can fix my 2 and turn it into a 3? Right, I can introduce more numbers to the problem, yeah.
For each clause, you add 2 numbers where it's just everything's a 0 except for 1 at that index.
Good, so we're gonna basically add like padding, right? If I just added like 2 freebies for the first clause, and it just had a 1 for that clause and 0 everywhere else, so that I can take my 1-point solution and turn it into 3. I can take my 2-point solution and turn it into 3. But a 0-point solution, I can only add 2, so I can only get up to 2. Right, so I can add kind of little padding numbers, not very interesting, but they just let you go from 1 to 3 or 2 to 3, but not from 0 to 3. Okay, so, right, that's the kind of like weirdo thinking that works. So for every clause CI, I'm going to create 2 numbers, 2 copies of the same number, which just has a 1 on that digit corresponding to the ith clause and 0 everywhere else. And I have 2 of them. So now if I have some sum, right, and I have, if I have a 3 in that slot already, then I don't have to use this at all. If I have a 2 in that slot corresponding to that clause, because I've taken 2 literals satisfying it, then I can just use one of these kind of buffer or padding numbers for that clause and just bump my score from 2 to 3 for that clause. If I have 1, then I can use both of them and bump my score from 1 to 3. But either way, any number that sort of satisfies any sum that satisfies the formula, so has greater than or equal to 1 for all the clauses, I can use the buffers to turn all those 1s and 2s into 3. But critically, since you only have 2 points to spare for every clause, you can't change a 0 into a 3. So at the end of the day, your sum, right? So this will be all 1s for the variables. But then what would this be for the clauses? Just to make sure we're on the same page. My target, what should I, 3. Yeah. So I'll do a value of 3 for all the clauses. Okay. And I did modulo 4 just so you can fit in 3. Okay, it could have been modulo 10 or anything bigger. Okay, so, right, so now you just check off the rules, right? So, right. Because the padding only gets you 2 points, the only way to get 3 for every clause is to get at least 1 literal for every clause. And because, for those last n digits, getting 1 means you took exactly 1 of the literals for each variable. Yeah.
One clause is like not able to be satisfied, but previous clause has 3 already, so you could add 2 of them.
Okay, this is a good question. This comes up every year. So first of all, so the question is this. So I have some clause here I just can't satisfy. It's always stuck at 0. Can I hack it by somehow like, taking a big number in the previous digit? Is that this side or this side? This side? Okay, so take this number and somehow like add extra points and carry over a 1? Yeah, that's certainly possible. Well, first of all, I could have just made it base 10 and that would have been okay. But even at base 4, we can get away with it. But why? So the idea is like, oh, I have 3 points here. Why don't I add 2 extra points, kind of carry stuff over or something? Or maybe just add 1 point and carry it over. Yeah.
That original plan would be a 3.
So yeah, so if you actually start adding points just to do this carrying hack, then you won't be able to get this one up to 3 anymore. So it'll barely work out. But if you don't want to be so clever, you could just done like base 10 or something, and then it's impossible to carry anyway. That wouldn't really change the essence of the problem. Okay. Good question. All right. Any other questions about the construction? Okay. So, all right. So that would be the whole reduction. I guess if I was going more slowly, I could. We would then want to do some kind of if and only proof, right? So if the formula is satisfiable, and I had some satisfying assignment x1 to be true, x2 to be false, x3, then here are the numbers I would take. I would just take the numbers corresponding to those literals, and then I would just write a sentence or two explaining why those numbers will add up to the target. Oh, I would take some numbers and I would have to take some padding. But at some level, you want to take your satisfying solution and construct the solution to the subset sum and explain why it is a solution to the subset sum, right? And then vice versa, if you had a solution to your subset sum, if I had a bunch of numbers and added up to something like this, here's how I would get an assignment. Well, I know that because those last digits are all 1s, for every variable, I'm taking either x1 to be true or x1 to be false. I'm only taking one of them. That's why I can, unambiguously set this one to be true or false, that one to be true or false. And it's going to be satisfied because the only way to get 3 for everyone is to choose at least one of those literals, and that means I'll take something to satisfy the clause for each one. So it's a little bit, by the time you get to this point, it might be not very interesting. But anyway, you just go from solution from one to the other, and then you'll get, then you'll really know that when you use this as a black box, yes really means yes, no really means no. Okay? So that would be the full thing. It's not super fun to watch me write it out, but that's what it would entail. Okay, so I think that is the whole proof, right? So what we've done is we showed that if you take a 3-sat formula, you can actually generate a subset sum problem, which is doing this trick where it's using all the bits to represent independent pieces of logic, essentially. And you can kind of encode an entire 3-sat problem into subset sum, right? Which is kind of crazy. Like, I think that when you look at just adding up numbers, you don't think of what all the bits, how the bits can kind of be exploited like that, right? You just think of quantities adding up, right? But in fact, you can pack in basically arbitrary logical puzzles because we know how to go from any sat formula or any circuit even to 3-sat, right? So we can like pack arbitrary logical puzzles into simple number adding problems, right? And so that sort of has lots of profound consequences. Okay. Any questions? Okay. We'll keep seeing more sort of problems that are sort of hiding complexity. Yeah.
So we can iterate to encode how many true tautologies were in each clause, right? Or how many of those were true in each clause?
Yeah. Okay. So what are the B numbers doing?
That's what we. Well, why don't we use 3?
So I made 2 copies of each B number just to make sure, and 3 because then if you had taken one literal, so you satisfied the clause just once, then you can add 2 of the B's to get up to 3, and then if you had 2, then you can just add 1. Whereas you can't subtract, so it made sense. If I'm choosing out of 1, 2, or 3, it made sense to choose the biggest one and then just add padding, because we don't have negative numbers in our problem. And I don't know if that answers the question. I mean, it's all maybe it's first good to appreciate at least the motivation, which is just that our first initial attempt, only set up a problem where to get a satisfying solution, each of those digits has to be at least 1. And this sort of at least 1 is not something that you can really encode naturally as subset sum. That's like a different language. But if we add this little hack of a trick where we add a little kind of free padding, for each of the clauses so that ones can be turned into 3 and twos can be turned into 3. Then I can set a target saying all of those have to be 3. And I can, and you know, we're just kind of struggling to produce an actual subset sum problem, right? And so we are doing these kind of roundabout things. Of course, this is not like we're not really coming up with useful algorithms in some ways, but we are making useful algorithmic comments about basic problems, right? We don't have a polynomial time algorithm to add up numbers to a target. You would think we would. That seems like a very simple problem, I would think, for most, right? And that, you know, if, like when my friends ask me like, what is theoretical computer science? I often use that as an example because it seems like such a simple problem that I can explain to people, you know, not in this room. And yeah, but yeah, we do contortions because we are going from one problem to another and we're just hacking to sort of, you know, yeah, what we're really doing is understanding subset sum deeper. Yeah.
So for the subset sum problem, I've seen the version where you're trying to find pairs of numbers that sum up the target, as opposed to just like an arbitrary subset.
Yeah.
That has a linear time solution, and that's
Sure.
that because it goes back into SAT.
Well, yeah, so okay, so here's a different problem that you can do an algorithm for. I give you a target and a list of numbers, find a pair of those numbers that adds up to your target. So clearly this is not hard to do. At the very least, you can try all pairs, right? And that's just n squared. But you can be even more clever. I guess this is like some kind of silly interview question. I don't know what kind of job this but anyway, if you want to do a little bit more clever algorithm, what would you do? You're just trying to find a pair of numbers that adds up to a target. So you could try all pairs, that's n squared. We'd be kind of happy with that. But you can do it faster. Yeah, if you sort the list, then you can kind of work outside in. Okay, whatever. But, okay, there is an algorithm. So why does that not contradict what we did? Because we said, oh, there's probably no polynomial time algorithm, or else you get a polynomial time algorithm for SAT. But there's some kind of polynomial time, even linear time algorithm we just described. So where's what's, you know, how do we kind of make sense of this? Yeah.
So of n times t, then here t would have some type of bound, right? So that should be over.
Well, even in this version where you choose two numbers, you can only choose two numbers. T could be really big. I can give you really big numbers in the input. So it's not because T is necessarily small in this pairwise subset sum problem. So we have two outs. Either that algorithm gives us a polynomial time algorithm for SAT, we should get all the Bitcoins. Or there's some difference there, in which case, what is the difference? Or where does the difference enter? Yeah. Yeah, the number of subsets. This constraint where you can only choose two numbers is a completely different problem. And you can see, like in the subset sum problem we picked, we created 2n numbers of which you choose n of them, right? So here you have to take a ton, and there's lots of possibilities. And there's only n squared possibilities to start. And if you're clever, you don't even have to check all of them, right? So it's the constraint where you only choose two numbers completely changes the complexity of the problem.
Yeah, and I was thinking, can you translate that into 2SAT as an idea?
Oh.
Can you do a reduction from that to 2SAT? And since we can solve 2SAT, that's why we can solve the pair, the target problem.
Okay, so the question is, can I take that pairwise problem and convert it to 2SAT? And at some level, I guess this is inspired by the fact that one problem has the word pair and the other problem has the number 2. And is that why one thing is fast and the other one happens to be fast? Well, I think first of all, directly, the reason why one problem is fast and the other problem is fast is because we just directly gave a fast algorithm here and a fast algorithm here. It is true that if you, I feel like the correspondence is a little bit different based on at least what we did. But if you took your pairwise subset sum problem and turned it into a 2SAT problem and sort of turning into 2SAT was very fast, and then you can run your 2SAT algorithm, then you will get another really fast algorithm for your pairwise algorithm. But I don't actually quite see how to map them very easily. So maybe it's doable with enough imagination. I think they're just fast insofar as we can easily come up with very fast algorithms. Well, two-side is not so easy, but we can come up with fast algorithms for both. Any other questions? I have like an exercise to kind of help expand on what's going on, but okay. I mean, at some level, like, okay, it feels like some very technical thing, but I think conceptually something crazy has happened, which is we have taken two unrelated looking problems and actually made a very strong connection. And the fact that subset sum, just adding up numbers, is almost arbitrarily difficult. It should make you think about what computation is, right? Something has happened just in one example. At some level, okay, all right. So here's maybe at least another exercise that doesn't have necessarily a long solution. So I thought it would be okay. All right, so let's look at like some relaxations, right? So subset sum we know is hard. But suppose I told you you could have a little bit of error. Okay, so I give you the same input, a bunch of numbers, a target, but you're allowed to be off by 1. Okay, in fact, maybe, yeah, so your goal is to see if there's a subset that adds up to t minus 1, t or t plus 1. So there's a little bit of, it doesn't have to be exact anymore. Almost exact subset sum or something. Question is, can we get an algorithm for this one now that we have a little bit of wiggle room? Or is this going to also turn out to be tough? Yeah.